This video is for my Algebra 1 class. It is over Lesson 36, Writing and Solving Proportions. So ladies and gentlemen, in the past, I have taught you, that is in past classes, I have taught you how to make proportions using what's called the ratio box. And basically the ratio box, we think about making a 2 by 2 box, and we typically label the first column as ratio, and then the second column is actual. But in reality, the actual values are really just a second ratio, just an unreduced ratio. So it's really ratio 1 and ratio 2. And then our ratios are comparing two different groups of numbers. And so the columns or the rows of our 2 by 2 box would be the first group of numbers and the second group of numbers. And we would fill in all the values there. So just for simplicity's sake, we're going to represent that here. Now notice that I did make a box though this time. So hopefully we've gone to the point now where we've gotten advanced enough that where we can leave the box behind, where we can still imagine the box, but just write the proportion. Now when it comes to abandoning the box, we could also look, instead of ratio, you could look at this as you're describing some sort of relationship between a quality between two different groups and another quality. Okay, so those are just different ways that we can look at those. However, as we abandon the box, we gain a little bit more flexibility. It turns out instead, I've got my first ratio and my second ratio. So instead of my first ratio being about some quality between group 1 and group 2, I could have the first ratio be a ratio between two things in the same group. And we'll see what this looks like in just a second. So then the second ratio would be a ratio completely related to the second group. Well, in this case, the numerators then would be corresponding qualities. We'll call them quality 1, whatever that is. It could be the length of something, could be the height of something, okay, width, whatever. And so it could be a ratio of two things in the same group compared to corresponding two things in a second group. And if we look at it from here, then we'd end up with a related ratio or proportion that would look like this. Now, if we think ahead, we hopefully remember how to solve proportions. We're going to cross multiply. Well, it turns out that the cross products here and there are the same. So again, we've got this flexibility. So as long as you're doing things in an organized manner, it should all come out okay. So is it a ratio describing one quality? So that quality could be the length of the smallest leg on a right triangle. So group 1 would be the one triangle, group 2 would be the other triangle. So we have the ratio of the smaller leg to the smaller leg from one triangle to the other triangle. Quality 2 then might be the ratio of their hypotenuses. So the hypotenuse of the one to the hypotenuse of the other. So let's take a look at a few more things, and then we're going to put this into practice. Next up is a vocab term, similar figures. Since that is a vocab term, let's go ahead and highlight that in yellow. Similar figures are figures with the same shape. Now, if we think about figures with the same shape, what controls the shape of a figure are its angles. So in order for two figures to have the same shape, all corresponding angles, because angles control the shape, all corresponding angles are congruent. If all corresponding angles are congruent, then their shapes will be the same. Now, ladies and gentlemen, you'll notice that this definition says nothing about the size. And this is actually an important detail. Because in mathematics, when we don't mention something, that means that that issue doesn't matter. So whether these have the same size or they're different sizes, it doesn't matter. It makes absolutely no difference as to whether or not they're similar. So you could have similar figures that have the same shape and are the same size, or you can have similar figures that are the same shape but not the same size. Both are possibilities. And so we can't say that their sides are their corresponding sides are congruent. Instead, though, what we can say, because they have the same shape, is all corresponding sides are proportional. So from one figure to another, if one side of one figure is twice as big as its corresponding side, then all the sides of one figure will be twice the size of their corresponding sides in the other figure. So speaking of similarity and twice as big, we're going to make a triangle here. Let's make a right triangle just for simplicity's sake. And I'm going to call this A, B, and C. And then next to this, I want to create another triangle that has approximately the same shape. Do the best to the best of your ability. We'll make this D, E, and F. And if we've done our job correctly, we should be able to say that triangle ABC is similar to, so there's my similar to symbol. It kind of looks like the top of a congruent symbol, or it looks like half of an approximately equal to. So triangle ABC is similar to triangle DEF. So just a reminder that when we say that two things are that they're similar, that the letters must be in corresponding order. And we do this in mathematics to communicate a lot of things very quickly and simply. And so the moment I see this statement in mathematics, I instantly know A corresponds to D, B corresponds to E, and C corresponds to F. So without even needing to look at the figures, I can tell you right now that angle A must be congruent to angle D, because A and D are corresponding, and corresponding angles are congruent. Therefore, I also know that angle B is congruent, and by the way, that's the congruent symbol, an equal sign with that same little mark above it. So angle B is congruent to angle E, so B and E correspond. And finally, angle C is congruent to angle F. Instantly, I know that just because of what's written here. Now, I know more than that, actually, because I also know that the corresponding sides are proportional. And then this is what I was talking about up at the top, where we've got some flexibility in our thinking. So let's say we choose a quality here to talk about, like the hypotenuse. Hypotenuse is pretty easy to identify. So maybe that's my first ratio is going to be a ratio of the two hypotenuses. So for my second ratio, let's make that the longer leg of each right triangle. Well, so from what to what are we making our ratio? What to what? Let's make it the larger triangle to the smaller triangle. And now as far as the homework goes, guys, when you're deciding this, you would decide on what to choose based on whatever a problem was asking for. Right now, I'm just making up an example, but you would choose based on what is it that you're looking at, what are you talking about, what information do you have, what information is missing. So, but just to put this together, so I've decided the first one's going to be a ratio of hypotenuses, so I have segment AB, which since we're talking about numbers here in the proportion, I'm going to make that the length of segment AB, or just AB. And so in the other one, I have DE. Well, the larger triangle is the one that has AB, and the smaller one is the one that has DE for its hypotenuse. So AB to DE is my first ratio. Now we're making a proportion, so this is going to be equal to another ratio. This ratio is going to be made by looking at their longer leg. So there's a longer vertical leg, a shorter horizontal leg. So the longer leg here, the length of that is AC. The length of this longer leg is DE. So on the larger triangle, I have AC. On the smaller triangle, I have DF. Now, ladies and gentlemen, let's say we were given an example where we are given the length of two of the legs on one triangle, one of the legs on the second triangle, but we're looking for the missing leg. So maybe it doesn't talk about the hypotenuses at all. And so we want to create a different proportion. In that case, I might choose instead to make the larger triangle my first ratio. So before, remember, that was our rows. It could become my column. So then the smaller triangle then, of course, would be my next ratio. So larger triangle, smaller triangle. So what are we looking at then if I don't have the hypotenuse? How can I describe those two other sides? Well, I can describe one side as being the longer leg, and the other side as the smaller leg. So if we've done this thinking, put it together, okay, so on the larger triangle, the larger leg is AC. On the larger triangle, the smaller leg is BC. On the smaller triangle, the longer leg is DF. And then on the smaller triangle, the smaller leg is EF. And we get another proportion. In fact, here, since there are three sides to this triangle, we could create an extended proportion. And so if we just keep comparing aspects from the larger triangle to the smaller triangle, we could compare hypotenuses. So on the larger triangle, we have AB. On the smaller triangle, DE. I could compare then the longer legs on each triangle. So longer leg on the big guy is AC. Longer leg on the little guy is DF. And then, of course, the third side, the smaller leg, would be BC on the big triangle and EF on the small triangle. Now, if we were able to plug in numbers or variables based on what we knew, what we didn't know into here, in order to solve this, what you would end up doing is you would just ignore one section of it. So if I ignore this section, I could potentially cross multiply and solve. If I ignored this, again, cross multiply, solve, or if we ignored that, cross multiply and solve. Now, ladies and gentlemen, if we were to take these numbers here and reduce them down to integers, we would get x over y, where x is some integer, y is some integer. Well, ladies and gentlemen, this simplified ratio, if we took all our numbers and just simplified them down, this right here is what's known as the scale factor. So the scale factor here tells us basically, with the larger on top and the smaller bottom, it would tell us how much larger the top is than the bottom. If we were to flip it around, it would tell us what fraction of the smaller guy is what fraction of the bigger guy. So with that being established, and again, we're going to use this in just a moment. Okay, so we're going to have a bit of a setup here, and then we're going to apply. So we've got similar figures there. We've talked about proportions in general. Next up, we have another vocab term called congruent figures. If you remember what congruent figures are, you should find it no surprise then that this is actually going to be the easier of the two. Congruent figures are figures with the same shape. So because they have to have the same shape, this means that congruent figures actually are similar figures as well. However, they have one more condition. Not just the same shape and size. And so now we do mention the size. And so it has to be that they have the same size in order to be congruent. Well, remember, if they have the same shape, then we know all corresponding angles are congruent. That's how you get the same shape. However, this time, since all the sides, or excuse me, they have to be the same size, it's the sides that control the size. So now all corresponding sides are congruent. So let's make a figure here, and then do our best to, it's a little too far out, do our best to make one that looks about the same. Now, because there can be human error when we draw, it is important to note that in geometry, you are only allowed to assume what has actually been marked on your paper. So if nothing has been marked as congruent, then you can't assume they're congruent. Now, these are both marked as right angles. You can go ahead and assume that they're right, that they are congruent. Now, up here in these pair of triangles, if I were to actually mark what I knew that these three pairs of angles are congruent, well, the right angles are simple, they're done. However, for angle B congruent to angle E, what we would do is we'd make a single curved arc in both of those angles. That single curved arc then tells me that all the single curved arcs are congruent to each other. And now here for angle A congruent to angle D, if I just do a single arc, then that's going to suggest that angle A, angle B, angle D, angle E, those are all congruent. We don't know that. We do know that B is congruent to E. We do know that A is congruent to D. So when I move up here to this other angle, I'm going to put two arcs in it. And so anything with a double arc would be congruent to anything else with a double arc. So down here, likewise, let's go ahead and make this G, H, and I. We'll make this J, K, and L. So right off the bat, I can see that it is already marked that I is congruent to L because that they're right angles and all right angles are congruent. So that's good. However, if I tell you that triangle GHI is congruent to triangle JKL, then you know by that statement, because it's going to be in corresponding order, just like the similarity statement was, we already know that angle G is congruent to angle J. So if I mark that, G congruent to J, so single arc, single arc. Now, we had our figures up here, and we're moved on to something else down here, so I can go back to using that single arc without it being congruent to some other pair of figures. All right, going on the corresponding order, H is congruent to K, angle H, that is congruent to angle K. And then finally, as we just discussed, the right angles must be congruent, so angle I must be congruent to angle L. I is last, L is last. So I'm going to put a double arc down here. Now, as far as the sides go, we can use this this congruent statement here to get our sides as well. So if I use the first two letters here, segment GH then will be congruent to, use the first two letters here, segment JK. If I use the second two letters, segment HI, therefore is congruent to second two letters, segment KL. If I have it wrap around, so the third wraps around back to the first, segment IG is congruent to, and again, take the last and the wrap around to the first, LJ, segment LJ. All right, so if we record these, segment GH, I'm going to put a single tick mark on GH, is congruent to segment JK, so I'm going to put a single tick mark, because it's tick marks that we use to label sides as congruent. Now, segment HI, then we're going to go to, a double tick mark, because we already used the single. So since this doesn't have to be the same as the first one, we use a double tick mark. And segment HI is congruent to segment KL, so that will also have a double tick mark. And then finally, IG, right here with 3 tick marks, will be congruent to segment LJ. All right. We're almost there. A few more things, and then we're going to see how to apply this. So next up, let's consider if we have one figure, call it figure 1, and if we have a second figure, let's call it figure 2. If we were to take the perimeter of each of these figures, a piece of 1 for figure 1, piece of 2 for figure 2, we could put it into a ratio and simplify it to x comma y, which remember is the scale factor. Well, ladies and gentlemen, if you know the scale factor for a linear measurement, just a normal plain old inches, feet, miles measurement, then we can also find the scale factor for their areas. And it's actually very simple. If you know x over y is the scale factor, square it. And that's the area. That will be the scale factor for your area. If this figure then were to be three-dimensional, and we wanted to compare their volumes, cube it. So by way of example, let's say, make a little chart here, perimeter, area, volume. So let's say we had a third figure, and a fourth figure. If I were to tell you right now that figure 3 has a perimeter of 6 units, has an area of 4 square units, and has a volume of 8 cubic units, and I were to tell you that the scale factor here is 3. Sometimes when we're dealing with scale factor, we use the letter K to represent this. Oh, I'm going to make a better K than that for you. So if the scale factor is 3 here, then what I'm going to do is I'm going to take the previous measurements, and we're going to say that figure 3 is the smaller of the two. This is the larger of the two. So in order to get larger, we're going to multiply. And we're going to multiply by the scale factor. Now again, like we talked about up here, for perimeters and other linear measurements like that, you've got your scale factor, so it's going to be times 3. For area though, it's the scale factor squared. So this will be 3 squared. And then times for volume, volume is cubed. So 8 times 3 cubed. So if we're to simplify this, if the perimeter of figure 3 is 6 and it undergoes a scale factor of 3, then its new perimeter will be 18. If its area used to be 4, but then it undergoes a scale factor of 3, its new area will be, well, 3 squared is 9 times 4 is 36. And then finally, if we start with 8 for the volume, scale factor 3, will mean that we're taking 3 squared and timesing it by 8. So 3 squared is 27 times 8 is 216. So ladies and gentlemen, with all that background, those basics in place, please open up your book and let's take a look at a few practice problems. So you will find this on page 226, 226. Here we go. A. The measure of triangle ABC is similar to, or excuse me, not the measure. Triangle ABC is similar to triangle LKM. Find the measure of angle K and the measure of angle C. So we need to find K, the measure of K, and the measure of C. In this case, what I would do is I would look for things that are corresponding. So when I look at this, first of all, K, I can see corresponds with B. And since these figures are similar, I know right away that the measure of angle K is equal to the measure of angle B. Because these figures are similar, their corresponding angles are congruent. In other words, their measures are equal. So whatever the measure angle K is, it's the same thing as the measure angle B. Well, look at the figure there, measure angle B is 25 degrees. Now this problem also asks us to find the measure angle C. So I start with measure angle C. Is there something that corresponds to C on the other triangle? And of course there is. It's the measure of angle M. Well, measure of angle M is 20 degrees. So therefore the measure of angle C must be the same thing. All right, B. The figures are similar. Find the scale factor. Then use the scale factor to find X. So the scale factor, ladies and gentlemen, is typically written with the larger value on top and the smaller value on bottom. So but first we got to look for what corresponds here. So for B, I see the right angle, okay? And then, so we got a right triangle. If we look at our right triangles, we've got 2 pairs of congruent sides there, or corresponding sides, 2 pairs of congruent legs. Well, choose a pair. So the 5 feet that's vertical on the left and the 3 feet that's vertical on the right, not because they're both vertical, but because they're both the smaller leg of our right triangle, makes them corresponding. So I'm going to have a scale factor then of 5 feet over 3 feet, which will really just become 5 over 3. So there's my scale factor. It says then use the scale factor to find X. So one of the things that we can do with the scale factor is we could actually use it to write our proportion. So if I start with 5 over 3, we got to do some thinking here. So 5 and 3 both come from the shorter leg of their respective triangles. The numerator comes from the larger triangle, the denominator comes from the smaller triangle. So what is it that we want to find? Well, we want to find x. X is the longer leg. So I'm going to make a new ratio comparing the longer legs of these two triangles. So I see x in one triangle, I see 5 feet on the other, so this is going to either be x over 5 or 5 over x. Well, which one comes from the same place as this 5? So this 5 is for the larger triangle. So over here, it's going to have to be x from the larger triangle. And then on the bottom, we've got our 3. 3 comes from the smaller triangle. So over here, well, what comes from the smaller triangle in the same spot? 5. A little cross multiplying. 3 times x gives me 3x. And we might as well do 5 times 5. It's easy enough. 25. Divide both sides by 3. And x equals, so 3 goes into that 8 times with 1 left over. But this is going to be 8 1/3 feet. All right, C. The side of a building casts a shadow 21 meters long. A statue that is 5 meters tall casts a shadow 4 meters long. The triangles are similar. How tall, is the man, how tall is the building? Well, ladies and gentlemen, we're going to make a couple of ratios. So we got to decide what our ratio is going to be. So we got a statue and we got a building. Because they're making right angles, we've got the height of each of them, we've got the length of the shadows, and we've got the hypotenuses. Well, I think if you look at the story problem, it's pretty obvious what we're going to leave out, the hypotenuses. Because one of them is the height of the object, the other is the length of its shadow. So I might organize my information here into my proportion by thinking about the building first. The other then will be the statue. So on the building, I've got the height of the building and I've got the length of the shadow. So maybe that becomes my proportion for the building. The height of the building to the length of the shadow. Well, for the building, I don't know its height. However, I do know the length of its shadow is 21 meters. And if all the units are the same, we can just leave them off and put them back on at the end. Okay. For my next ratio, the statue then, the height of the statue is only 5 meters. And the length of its shadow is 4. So now, let's cross multiply to solve. So if I cross multiply here, 4x is what I'm going to get first. On the other side, 21 times 5. Well, I know 5 times 20 is 100, plus one more group of 5, 105. Divide both sides by 4. Therefore, x must equal, and 4 goes into 10 2 times with 2 left over. 4 goes into 25 6 times with 1 left over, and of course 1 left over when they're fourths would be 25 and meters at the end here. So I'll circle my answer. Now, ladies and gentlemen, we could have set this up differently. So instead, I could have considered my first ratio to be the heights of each figure, the second to be the length of their shadows. And so in this case, I would have had the building compared to the statue. Building compared to the statue. So if we were to arrange it this way, so the height of the building was unknown, sorry. The height of the building was unknown. The height of the statue was 5 meters. The length of the building, the length of the shadow of the building, was 21 meters. And then the length of the statue's shadow was 4. And again here, if we were to cross multiply, 4x equals 105. So as long as you're organized, you don't really need the box anymore. D. The scale drawing of a kitchen tabletop has dimensions 5 inches and 2.5 inches. If the scale factor of the drawing is to the actual table is 1 inch to 18 inches, what are the dimensions of the actual table? So in this case, we know that our ratio, our scale factor is 1 inch to 18 inches. So 1 inch would be on the drawing. So the 1 inch would be the drawing, the smaller amount. So the 18 inches would be the actual real life amount. And so I know 1 to 18 here. Now with 1 being the drawing, so we said earlier that this drawing had a dimensions 5 inches by 2.5 inches. So we have 5 inches on the drawing, but we don't know what that is in real life. Well, a quick little cross multiplying. 1 times x is just x, and 5 times 18 is 90. So that'll be 90 inches long. But then we also know that the width is 2.5 inches. And again, cross multiply x, multiply those together. And if I multiply those together, I'm going to get 45 inches. So what are the dimensions of the actual table? 90 inches by 45 inches. All right, ladies and gentlemen, we're going to come up here and do E. And E is our last one. So for E, we're told that small toy cars are constructed using a scale factor of 1 inch to 64 inches. What is the ratio of the area of the toy car and the actual car? So we're just switching from a linear measurement, just scale factor is a linear measurement, to then the ratio of the areas. So remember, ladies and gentlemen, in order to do that, we're just going to take each value and square it. So if the original scale factor was 1 inch to 64 inches, if we just square both of them, then we get the area. If you want the ratio of the volumes, cube each of those. So the first one, 1 inch squared, should be easy, becomes 1 square inch. For the other though, 64 times 64, a little bit harder. Work it out. you get 4,096 square inches. If we were looking for something having to do with volume, we would cube them instead of square them. And that, ladies and gentlemen, is the end of our lesson.